let's apply Snell's law to a flat interface. Okay, so let's remind ourselves Snell's law is n1 sine of theta 1 equals n2 sine of theta 2. And what that means is if this is an interface, let's say water and air or something, and light is coming off of something in the water, let's say I have a penny in the bottom of a cup. So there's my penny, and light's coming off of it, and I'm seeing it, I'm viewing it from above. So light's coming off the penny, N1, into the air, N2. Right? And it will bend according to Snell's law. The light will bend off of it. Now, to do this next derivation, we need to understand that the light rays coming from this penny into my eye are not deviating that much. There is an angle, and it obeys Snell's law, but it's really a small angle. So, I mean, if you imagine, here's my eyeball up here, and especially my pupil is the only place where the light actually comes in. If I were to draw a light ray from the bottom of this cup, where the penny is, to the surface, and it bends following Snell's law, I mean, I can't even draw it here. It's so small, you know, and it bends, comes over my. I really am not doing this justice at all because it's such small angles. You know, the normal line is nearly parallel with the rays themselves. Now, truly, it is bending, but I can't draw it. Now, that's okay. I'm going to exaggerate a picture over here, but I'm going to note that these thetas are small. Theta is very small. And that allows us to use an approximation that is very good, that says that sine of theta is equal to tangent of theta. Okay? And so when theta is super small, as it is in this case, then sine of theta equals tangent of theta, and we can rewrite Snell's law saying n1 tangent of theta 1 equals n2 tangent of theta 2. Right now it doesn't seem like that's any benefit, but we'll see in a moment that it is. So I'm going to redraw this now, totally exaggerating the angles these are making. So here's my interface, alright, and here's this penny. I'm going to draw a dotted line just to represent what is straight above that penny. And here's a ray of light coming to the surface. And because N1 is greater than N2, I know that that is going to bend away. Alright, so it's coming towards the surface and bends away, going that way. Okay, now I could draw another one that's coming this way symmetrically and bending away that way. I'm going to not do so for clarity, but the important thing is that this ray is what enters my eye. That's this one right here. It enters my eye. Now when it enters my eye, all I can tell is that it came from this direction. So my eye sees it as if it came from back here along that line. And a similar one that bent this way would have come back and converged right there. And where those rays converged is where the penny appears to be. That's where my eye thinks it came from, okay, because of that straight line effect. So my question is, say, well, the penny truly is that far below the water. I'm going to give that a variable s, below the surface of the water, but it appears to be only that far below the water. I'm going to call that s prime. And s and s prime are usual variables for image or object and image location. So this is our object location and image location. We'll use those a lot in a study of optics. So my question is, how does s prime relate to s? If the penny is truly 5 centimeters below the water, then what is s prime? How far does it appear to be? If I know what the index of refraction of the water is and the air. Okay, so this is now a geometry problem. I'm going to use Snell's law to define these angles here. This is theta 1, and this is theta 2, okay, according to our definitions of Snell's law. And now some geometry. This is a vertical line, and that is a vertical line, and this is a straight line that intersects both, which means we have some rules of geometry that says that angle there is also theta 1. Okay, it's these opposite angles there. By same argument, this angle here is theta 2, because that is a straight line that is intersecting these two vertical lines. we have theta 2 there, theta 1 here. We have s prime being the length there, and s just unprimed being this full length down to here. Let's just choose a dummy variable, x, being the length of this side of these two triangles. I'm going to draw that one. So we have this triangle, and then I have this triangle. I have two triangles that I'm going to be analyzing. Okay. So, looking at these triangles, I can say that tangent of theta 1 is going to be opposite over adjacent. So tangent of theta 1 is equal to the opposite x over adjacent, which is s. And I can also say tangent of theta 2 is opposite x over adjacent s prime. And now that I have those definitions for tangent of thetas, I can come over here to my approximate definition of Snell's law, and I can say n1 x over, let me look this up slightly, x over s equals n2 x over s prime. And it didn't matter what x was because it cancels out on both sides. And that allows me to now solve for s prime. S prime, multiplying that up, is going to be s n2 over n1. Okay. I want to write that up here because that's kind of our main result. S prime equals s n2 over n1. Alright, now let's think about this. This is a good result. This would be a nice result to be able to use and apply to different problems. But let's think about what this means. So when light is coming out of a higher index material into a lower index material, the rays bend away from this normal, which means the line of sight must be closer to the surface than the object truly is. Okay? So this says n2 is the smaller one, and 1 is the bigger one. And so this n2 over n1 must be a fraction smaller than 1, and therefore s prime is smaller than s. That makes sense. Now we didn't do it here, but let's assume that this was light. I'm in the water, and light, I'm looking at a penny above the water. So light's traveling from the air to the water. Well, now n1 is air, that's 1, n2 is water, that's 1.33, so that's a fraction bigger than 1. That says s prime ought to be bigger than s, or the apparent position is bigger than its true position. Okay, now let's put my eyeball down here, and light's traveling from air into water, and so the light's going to bend towards the normal. Okay, now I'm going to leave it for an exercise for you to see that the true position would definitely be smaller than the apparent position because of how that light is now bending towards the normal. So it's a kind of a reverse of this process. Okay, but it does make sense, and now we can analyze problems if we're careful to know what s prime means, what s means, and how to differentiate which is 2 and which is 1 for our index of refraction.